with Neptune raising worries among investigators and space fans. Notable specialists including Neil deGrasse Tyson and Michio Kaku have sounded alarms about the potential aftereffects of this famous battle. But how did Pluto end up on a crash course with its distant neighbor? And what might this perpetual mishap mean for us here on Earth? Can we investigate this unfolding event? Once remembered to be an undeniable planet, Pluto was subsequently renamed as a dwarf planet because of its unique orbit. Regardless of this change, it continues to captivate and draw in stargazers. Advancing appraisals from undeniable experts highlight a focusing region between Pluto's way and that of Neptune. These educated authorities warn against a logical mishap between the two planets, addressing a basic risk to Earth. Pluto's journey around the Sun is distinct due to its unrivaled characteristics within our planetary framework. Its orbit ranges in width from the time of its discovery in 1930. Pluto still truly can't complete a full orbit. Adding to its intrigue is the entirely twisted condition of its orbit, a departure from the primarily circular orbits of the major planets. In addition, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making it more outrageous than other planets. One unique aspect of Pluto's orbit is its intersection point with Neptune's path. For nearly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, contradicting assumptions about their explicit positions in the Sun-centered system. So why hasn't a crash occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The examination of Pluto's orbit began not long after its discovery, presenting a puzzling course for astronomers. Instead of the majority of the planets, whose orbits change relatively close to the ecliptic plane, Pluto's unique elements include a gaudy tendency and a round shape. The mystery arises with the acknowledgement that Pluto's orbit crosses that of Neptune. The behavior of Pluto's orbit amid these complexities serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves charting the development and gravitational interactions among three prominent bodies, like Pluto, Neptune, and the Sun. This issue explains the complicated exchange of their trajectories and gravitational forces. Terms like non-synchronous libration, scope libration, and the Kozai mechanism add to unwinding this brilliant riddle. Astrophysicists assert that odd libration, which is responsible for keeping planets in their orbits, plays a significant role in the unique situation of Pluto and Neptune. This term suggests that when Pluto intersects with Neptune's orbit, it is positioned about 90 degrees away from Neptune, which is crucial for preventing potential collisions. Scope libration ensures that when Pluto draws near to Neptune or other giant planets, it is oriented so that it remains on their orbital plane, providing an additional layer of protection against crashes. The Kozai mechanism explains why Pluto's orbit around the Sun appears chaotic but remains stable over time despite apparent irregularities. Mathematical simulations in the late 1980s revealed that despite consistent properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to significant variations over extended periods. Nevertheless, Pluto's strange orbit maintains stability over very long timescales, keeping chaos under control. Consistent programmatic observations have improved our understanding of how massive planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, contributes to the stability of Pluto's orbit. Similarly, Jupiter's massive gravity exerts a significant influence, while Saturn's effect, though more subtle, also plays a role. Through rigorous examinations, researchers have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable progression of Pluto in space for billions of years. These quirks are vital for maintaining the control and consistency of celestial dynamics in the universe. Without these factors, the solar system would be prone to greater chaos and instability, potentially leading to collisions or ejections from stable orbits, which could have progressively escalating impacts on other celestial bodies. Understanding Pluto's orbit is particularly significant amid discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the unique nature of the neighboring planetary system. Pluto's case highlights how seemingly unstable orbits can achieve equilibrium through the complicated interaction of gravitational forces and orbital mechanics. Consistent observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Investigating the depths of space often reveals the irregular nature of celestial bodies. Furthermore, Pluto's orbit serves as an excellent illustration of this unpredictability. The concept of orbital chaos clearly demonstrates the delicate reliance of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the planet's position or speed can decisively alter its long-term orbit. Simulations have been instrumental in helping experts understand how Pluto moves in space by making minor adjustments in these simulations. Minor changes can have a critical influence. In the last part of the 1980s, these recreations uncovered a fascinating part of Pluto's way. Regardless of highlights like non-simultaneous libration and scope libration adding to its stability, Pluto's circle can still show unconventional changes, as even slight varieties in Pluto's position or speed can prompt significant changes in its direction over many years. Despite this inherent complexity, Pluto's circle remains stable for an exceptionally long time, maintaining intelligibility over billions of years. This suggests that, underneath its apparently conflicting appearance, Pluto's excursion around the Sun follows a planned order, reflecting phenomenal events. Particularly with planets like Pluto, which have surprising circles, the inherent idiosyncrasy of these designs makes long-term forecasts questionable. Mathematical reenactments assist us in understanding and predicting the future developments of celestial bodies. However, they also reveal the limitations of our forecasts. These models heavily depend on accurate initial conditions and replicate complex interactions. Even a slight error can lead to unfathomably different results, making exact predictions challenging. The tumultuous nature of heavenly circles like Pluto serves as a reminder of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our consistently limited knowledge. The boundlessness of interstellar distances and the shortage of planets in open space act as barriers against constant impacts. Additionally, rogue planets are relatively intriguing compared to the number of stars and planets in stable circles, making such encounters even less likely. Understanding the gravitational impacts of giant planets on Pluto's circle provides significant insights into the broader dynamics of the adjoining planetary system. It illustrates how each planet's presence and position can influence the stability and direction of different bodies within the system. Notwithstanding these complex forces, notable astrophysicists are expressing concerns about a potential impact between Pluto and Neptune. This raises questions about why such an influence, which seems far-fetched given these multifaceted dynamics, is still a subject of concern. Neil deGrasse Tyson, a prominent astrophysicist, offers a remarkable perspective on the complexities of our adjoining planetary system, especially regarding Pluto. Tyson, known for renaming Pluto as a dwarf planet rather than a planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson sees Pluto's renaming not as a diminishment but rather as an important affirmation of our expanding knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He views the intricacies of orbits like Pluto's as a demonstration of the vast depths yet to be explored in space. Tyson believes that the allure of space makes astronomy so compelling. Moreover, Tyson recognizes how space-related events and discoveries impact public interest in space science. He thinks events like Pluto's renaming and its unconventional orbit provide opportunities to capture the public's imagination and interest in the universe. By examining the dynamic and sometimes odd aspects of celestial mechanics, Tyson aims to foster a deeper understanding and enthusiasm for the universe. Neil deGrasse Tyson opens a window for the general public to feel overwhelmed by the wonders and mysteries of the universe. Working alongside researchers, Tyson actively warns the public about the possible risks of Pluto's whimsical orbit. After extensive investigation of Pluto, he has raised concerns that the three-body problem could pose a real threat, suggesting that a collision with Neptune is not an exaggeration. Furthermore, Tyson emphasizes how such an accident could disturb the equilibrium of the universe and lead to catastrophic outcomes affecting Earth. An impact between Pluto and Neptune would be an unprecedented and disturbing event in our adjoining planetary system. This effect could release an enormous amount of energy, potentially destroying Pluto. Its more modest size and cold structure garbage from the crash could dissipate across the planetary group, presenting potential dangers to different planets and their moons. For Neptune, such an effect could possibly modify its environment and orbit contingent upon the particular subtleties of the impact. Michio Kaku, an unmistakable hypothetical physicist known for his work in string theory and scientific advancements, offers an interesting viewpoint on this present circumstance. His perspectives on the conceivable destiny of space investigation and the connection between quantum mechanics and hypothetical physics provide significant insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a brief investigation of the possible future of space exploration. Understanding the complex gravitational interactions and orbital elements of heavenly bodies like Pluto, according to Kaku, can offer vital insights for future space missions. This knowledge can help navigate the planetary group more effectively, anticipating possible dangers and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the models derived from studying Pluto's orbit can be applied to investigate other heavenly bodies, providing a framework for approaching and understanding distant worlds. In examining the actual mechanics of planets, Kaku frequently highlights the critical connection between celestial mechanics and theoretical physics. He believes that the interactions and movements of planets, like the gravitational dance between Pluto and Neptune, are not isolated events, but are connected to fundamental principles of physics. Kaku's work in theoretical physics, especially in string theory, aims to explain these principles at a fundamental level. He suggests that considering the intricacies of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also expressed concerns about the potential crash, connecting it to his theories about the universe. He believes that if Pluto and Neptune were to collide, it would be a critical event in space science, offering a striking observational opportunity that could potentially enhance our understanding of string theory. String theory, a hypothetical framework that replaces point-like particles with one-dimensional strings, endeavors to describe the fundamental forces and matter in the universe. The impact of such magnitude within the neighboring planetary system could create unusual states of energy and gravity, providing insights into the behavior of fundamental particles and forces under extreme conditions. A key focus in string theory, in addition, is the gravitational waves generated by the crash, which could provide critical data for testing hypotheses related to string theory, gravity, and space-time. While the immediate effect on Earth would be negligible due to our distance from the outer neighboring planetary system, the extensive outcomes of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as depicted by string theory and other fields of theoretical physics. Pluto's orbit serves as a striking representation of celestial mechanics, demonstrating both stability and chaos within our neighboring planetary system. The remarkable qualities of its orbit are affected by the gravitational forces of neighboring planets, especially Neptune, highlighting the complicated and dynamic nature of space. The universe holds quite a number of secrets, and the three-body problem is only one of them. There are other potential disasters that researchers expect. While the potential results of planets crashing in space are incredibly low, it isn't altogether doubtful how planetary orbits are affected by various factors, including gravitational interactions, which can be understood from the perspective of the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythmic setup driven by orbital resonances. Over time, these patterns can make planetary orbits less stable, potentially leading to crashes. Notwithstanding the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Researchers eagerly monitor these systems to determine how planets influence each other's orbits, particularly when they are in close proximity. This knowledge helps us appreciate the evolution of planets in space. Rogue planets, floating through space without orbiting a star, present an additional eccentric component. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events, such as the close passage of another star or dynamic instability in different systems. Over time, these wandering planets can navigate immense distances, potentially arriving at locations far from their origin. During their solitary journey, there is a chance of them encountering other star systems, if one of these rogue planets enters another nearby planetary system, there is a remote chance of a crash with a planet in that system. However, given the vast and predominantly empty nature of space, the probability of a rogue planet directly impacting another planet is very low.